Chemistry, we're moving on to lesson 17, dealing with a concept called the Lewis Dot structure. So Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So here's a beryllium atom as we would diagram it using the method that we've learned earlier. So the Lewis dot structure simplifies this a little, and we'll show you what that is. So first you write the atomic symbol for beryllium, Be. Then you draw only the valence electrons around the symbol. So the valence electrons, of course, are the outer orbital electrons. Those are the ones that do the bonding, those two electrons you see in the second orbital. First orbital electrons don't get involved in bonding, so we don't draw them. So we simply place the electrons, and this is why I had you place the electrons around the atoms the way I did, because this will help you to draw the Lewis dot structures. So we'll go ahead and place those two electrons. And that's the Lewis dot structure. It's just that simple. So Lewis dot structures show only valence electrons, since only these electrons are involved in chemical bonding. So Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So we'll do the Lewis dot structure for oxygen. You can probably do this one yourself. So write the atomic symbol and then place the electrons, only the valence electrons. And that's the Lewis dot structure for oxygen. One more, phosphorus. And that's the Lewis dot structure for phosphorus. Again, the important fact of that is that there are 3 unpaired electrons, and that's where chemical bonds can take place. So the Lewis dot representation for a water molecule is shown here. So all atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with hydrogen if hydrogen shares its electron with oxygen. That's where they're going to join, and there goes the hydrogen, just as we saw in the previous lesson. Oxygen repeats this process with another hydrogen, and there it is. And that's a water molecule. Both hydrogen atoms and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. Covalent bonds form independent structures called molecules. Fluorine with 7 valence electrons bonds as shown below. There's the empty space, there's the empty space. And they come together. So now both fluorine atoms have an octet, sharing the 2 electrons in the middle. Okay, so each oxygen atom below has 6 valence electrons for a total of 12. But how do you create 2 octets from 12 electrons? Think about that. 2 octets should require 8 plus 8. That's a total of 16 electrons. Here you only have 6 valence electrons in each oxygen for a total of 12. So how do you form 16 electrons from only 12? Well, you don't. But how do you form 2 octets? That you can do. So let's see how that. Think about it. How would that happen? So there we go. Each oxygen shares both of its unpaired electrons to form what is called a double bond. That's in the yellow square below. Notice that each oxygen has 8 electrons in its valence orbital, because the electrons in the yellow area are counted for both atoms. So the oxygen on the left counts those 4 electrons in the yellow, plus the 4 others that are in its second orbital. Same with the oxygen on the right. It counts those 4 electrons in the yellow square, plus the 4 electrons that are in its second orbital over on the right. So that's how this works, and that's called a double bond. Double bonds are shorter and stronger than single bonds. So the Lewis dot structure for the O2 molecule looks like this. So in a covalent bond, electrons that bond 2 atoms are called bonding electrons. Electrons that do not bond 2 atoms are called non-bonding electrons or lone pair electrons. We tend to use both of those terms, and they mean the same thing. A pair of bonding electrons can be represented by a line. So each of those lines represents 2 electrons. Since you have 2 lines, there's the total of 4 electrons that you see above. Now the line should not be used to represent lone pair electrons. Oftentimes when you use the line notation like this, you don't even show the lone pair electrons on the outside. It would just be O, 2 lines, O, and that's all. Carbon dioxide, CO2, is what you exhale when you breathe. How does a carbon bond form with 2 oxygens? So there are a total of 16 valence electrons. You can see there, you can count them, between the 2 oxygens and the 1 carbon. So how do you form? So everyone needs to have an octet. So how do we do that? By creating double bonds between the carbon atom and each of the oxygen atoms, octets can be formed around each atom. So count it, convince yourself that all 3 of those atoms have an octet, where the electrons that are shared, that are bonding electrons in between the carbons and the oxygen, the carbon and the oxygens, count for both the carbon and the oxygen. So there's 8 electrons in the oxygen on the left, 8 electrons for the carbon in the center, and 8 electrons for the oxygen on the right. So carbon forms double bonds with each oxygen. This provided octets for all 3 atoms. You can have as high an order as triple bonds. You can't go beyond triple bonds, but there are some molecules that do have triple bonds. We'll see those very soon. The Lewis dot structure of a carbon dioxide can be drawn with the line notation to represent a pair of bonding electrons. Carbon dioxide, CO2, has a balanced charge. The 2 oxygen atoms pull equally on the 2 oxygen atoms pull on the electrons equally, so the charge is equally distributed. Carbon dioxide, CO2, has a balanced charge. The 2 oxygen atoms pull on the electrons equally, so the charge is equally distributed. When electrons are not pulled to one side of the molecule, then the molecule is said to be nonpolar. So you recall water is a polar molecule because the electrons are pulled over to one side of the molecule. Carbon dioxide, in this case, is a nonpolar molecule. The electrons are not pulled to either one side or the other. So let's review. We've talked about in the last few units, we've talked about ionic and covalent bonds. So these are some characteristics of the 2 different types of bonds that you should know. So first of all, the unit of each ionic compounds is called a formula unit or a unit cell, and they form crystal lattice structures. Covalent bonds form independent structures called molecules. One molecule can separate from another molecule in a covalent bond. Bond formations. Ionic bonds pass electrons. One of the atoms becomes the anion, one becomes the cation, positive, negative, and they stick together. With covalent bonds, they share electrons. The elements involved, ionic compounds, are a metal and a nonmetal. Covalent bonds are 2 or more nonmetals. You can have quite a few atoms in a covalent bond. Physical state, ionic compounds are solids. Covalent bonds can either be solid, liquid, or gas. Melting point, ionic bonds are generally higher in melting point, above 300 degrees centigrade. Covalent bonds are below 300 degrees centigrade. And solubility in water. Do they dissolve in water? Ionic compounds dissolve well in water, generally speaking. Not all do, but generally speaking they do. Covalent compounds don't dissolve in water, generally speaking. And conductivity, that means how well does heat or electricity pass through them, but generally we think of it as meaning electricity more than heat. Ionic compounds pass electricity very well, and covalent bonds do not pass electricity very well. We'll do a few mini experiments, mini labs to demonstrate some of these principles at a later time. And finally, we're going to spend one slide on metallic bonds. We're going to talk about them very little, but you should understand they are the third of the three types of bonding. So we're going to spend this slide to learn about them. So in a metallic bond, electrons are attracted to the protons in the nucleus, but the electrons are not held closely to any particular atom, so they jump from one atom to the next when they are pushed. Copper, abbreviation Cu, has a low ionization energy, so it easily passes electrons from one copper atom to another. The yellow Cu circles represent the nucleus of a copper atom and all of the core electrons. So the blue electrons you're seeing there are just valence electrons. The blue circles represent the copper valence electrons. So there they go. They go swimming around like that. So this is called the electron sea model because the electrons move around like fish in the sea. So since they have low ionization energy, they can be pulled away from their atom easily. But remember, all of those coppers have equal electronegativity and equal ionization energy as all the other copper atoms, so they don't stay with another copper atom very long. They'll just keep jumping from copper atom to copper atom. That was the analogy I used earlier about frogs on a lily pad. Frogs can jump around from one lily pad to another to another. And so this is that model, the electron sea model. That's how metallic bonds are formed. You don't need to understand any deeper than that. Why do the electrons flying around cause the atoms of a metal to bond together? But just understand that they do, and this is how it happens. So quick review of the bonds. Ionic bonds are between metals and nonmetals. Covalent bonds are between nonmetals and nonmetals. And metallic bonds are between metals and metals. And that takes care of this lesson on Lewis dot structure. You may ask, what's the point of Lewis dot structures? It's nice. They're nice, simple representation. You'll find out in this class you can do some pretty sophisticated analysis on a molecule based on its Lewis dot structure, and we'll learn that in a few weeks.